February 23, 1945. Stalag Luft Three, Sagan, Germany. Hauptmann Klaus Fischer stood in the frozen compound watching American B-17s pass overhead at an altitude he estimated as 24,000 feet. Fischer had designed components for the Messerschmitt Bf 1-10 before his capture in North Africa. He understood aeronautics, ballistics, and the mathematical impossibility of what he was witnessing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. From that altitude, in winter wind conditions, hitting a specific factory building should have been impossible. Yet, intelligence reports filtering into the camp spoke of American bombers consistently placing ordnance within 100-foot circles, from heights exceeding 25,000 feet. The German engineers among the prisoners exchanged knowing glances. Such precision defied everything they understood about high-altitude bombardment. 3 months later, Fischer would board a Liberty ship bound for Camp Butner, North Carolina. Within weeks of arrival, he would request assignment to the camp machine shop, where American guards would casually discuss formation bombing techniques. What Fischer learned there would shatter his understanding not merely of American technological capability, but of the industrial philosophy that made such capability possible. He had been trained to believe German engineering represented the pinnacle of human achievement. He would discover that America had approached the problem of precision bombing from an entirely different direction, one that German military doctrine had never considered, and that this approach had been operational since 1943, 2 years before he first witnessed its results. The story of German engineers encountering the Norden Bombsight represents more than technological surprise. It reveals a fundamental collision between two engineering philosophies. German aviation engineering, descended from Junkers and Messerschmitt, emphasized individual aircraft performance, pilot skill, and mechanical elegance. American aviation engineering, descended from Ford and Douglas, emphasized mass production, standardized training, and distributed complexity. The Norden Bombsight embodied this American philosophy completely. It was not the most elegant solution to high-altitude bombing. It was the solution that could be mass-produced, operated by adequately trained personnel, and maintained under field conditions. For German engineers educated in a tradition that prized theoretical perfection, this represented an incomprehensible approach to military technology. The Geneva Convention's provisions regarding prisoner treatment extended to professional respect for captured specialists. German engineers, like medical personnel, retained certain privileges based on their technical education. American military intelligence recognized the value of technical specialists among prisoners and established programs, allowing them to work in machine shops, maintenance facilities, and technical roles where their skills could be utilized. This policy, motivated by both Geneva Convention requirements and practical labor needs, would inadvertently expose German engineers to American manufacturing methods, quality control standards, and most significantly, to casual discussions of technologies they had believed were German military secrets. The journey to American captivity began with the collapse of the Afrika Korps in Tunisia during May 1943. Among the 275,000 German and Italian prisoners were significant numbers of technical specialists, engineers who had maintained equipment in desert conditions, designed field modifications, and adapted German technology to African warfare. These men possessed graduate-level technical education, practical battlefield experience, and deep confidence in German technological superiority. The Technische Hochschulen, Germany's technical universities, had produced generations of engineers who believed their education represented the world's finest technical training. This belief was not unfounded. German engineering had produced the Autobahn system, the Volkswagen, advanced chemical processes, and military equipment that had conquered most of Europe. The engineers among the prisoners carried this professional identity across the Atlantic. The Atlantic crossing provided the first indication that American industrial capacity exceeded German estimates. Liberty ships, welded rather than riveted, mass-produced at rates that seemed impossible, carried prisoners in conditions that contradicted their expectations. The meals served during transport, while simple, appeared in quantities suggesting unlimited supply. One prisoner, later identified in declassified intelligence reports as an automotive engineer from Stuttgart, recorded in a diary smuggled through processing that the transport ship's galley equipment alone represented manufacturing capacity equivalent to a medium-sized German factory. The observation was dismissed by fellow prisoners as exaggeration until they reached American processing centers. Camp Butner, North Carolina, established as a major processing and detention facility, would become home to thousands of German prisoners, including significant numbers of technical specialists. The camp's machine shops, maintenance facilities, and industrial work programs required skilled labor. German engineers volunteering for technical work assignments discovered workshops equipped with tools, measuring instruments, and materials that exceeded what they had available in Germany even before the war. The machine shop at Camp Butner contained a Brown and Sharp universal milling machine, a Cincinnati centerless grinder, and a Jones and Lamson turret lathe, equipment representing the highest standard of American precision manufacturing. German engineers recognized these machines instantly. Several were trained on similar equipment manufactured in Springfield, Massachusetts, that German tool companies had imported during the 1930s. What surprised German engineers was not the quality of American machine tools, which German technical literature acknowledged, but the casual abundance. The camp machine shop, serving a prisoner population's maintenance needs, possessed equipment that in Germany would have been reserved for critical military production. The implications were discussed quietly among technical prisoners. If a prison camp machine shop contained such equipment, what did actual American military production facilities possess? The question would be answered through observation, conversation, and eventually through direct exposure to American aviation technology. The machine shop supervisor at Camp Butner, Master Sergeant Robert Halloway, had worked at Pratt & Whitney before military service. Halloway's approach to prisoner technical workers reflected American industrial management philosophy. He provided clear specifications, adequate tools, and evaluation based purely on work quality. German engineers discovered that American technical supervision emphasized results over methods. If a prisoner machinist could hold tolerance within 0.02 of an inch, Halloway did not care what sequence of operations achieved that tolerance. This approach contradicted German technical education, which emphasized specific methodologies and theoretical understanding before practical execution. German engineers had been taught that understanding why a process worked mattered as much as making it work. American supervision seemed to assume that making it work proved sufficient understanding. The philosophical difference extended to technical documentation. German technical drawings, produced by specialized draftsmen, contained elaborate detail and precise specifications. American shop drawings, often sketched by machinists themselves, contained minimal information, assuming the machinist possessed standard knowledge. German engineers initially interpreted this as imprecision until they observed American machinists consistently producing parts to specification from minimal documentation. The realization came gradually. American technical education emphasized practical problem-solving over theoretical completeness. The system assumed competent practitioners rather than comprehensive documentation. By summer 1945, Camp Butner's machine shop employed 43 German prisoners with technical training. Among them were 2 mechanical engineers from Daimler-Benz, a hydraulics specialist from Heinkel, an optical engineer from Zeiss, and multiple machinists from various German industrial firms. The concentration of technical expertise created an informal technical community within the camp. Prisoners discussed engineering problems, debated technical solutions, and maintained professional identity through technical conversation. American supervisors, recognizing this community's value, occasionally brought actual problems for discussion. Broken equipment, maintenance challenges, and process improvements became collaborative efforts between American supervisors and German technical prisoners. It was through such collaboration that the subject of precision bombing first emerged in technical rather than merely observational terms. Master Sergeant Halloway, attempting to explain why a particular aluminum casting had failed, mentioned that the casting technique came from aircraft component production. The bomber production program, he noted casually, required manufacturing precision that automotive production had never demanded. A German engineer asked what precision. Holloway responded that bombsight components required tolerances of 5/10,000ths of an inch, maintained across production runs of thousands of units. The German engineers exchanged glances. Such precision in mass production seemed impossible. Holloway, interpreting their silence as incomprehension, explained that the Norden Bombsight alone contained 2,000 precision parts, each manufactured to tolerances that required specialized measuring equipment. The conversation shifted. The optical engineer from Zeiss asked what type of optical system the Norden employed. Holloway, bound by security regulations, stated he could not discuss specific details, but could confirm the system utilized a stabilized optical telescope coupled with an analog computer that calculated ballistic trajectory in real time. The mechanical engineers from Daimler-Benz immediately recognized the engineering challenge. A stabilized platform at altitude, subject to vibration, temperature variation, and aircraft movement, calculating trajectories for bombs with specific ballistic coefficients, all while maintaining optical precision, represented an extraordinary technical achievement. More significantly, mass-producing such a system with consistent performance characteristics seemed beyond current manufacturing capability, German or American. Holloway's response revealed the core difference between German and American technical philosophy. He explained that the Norden was designed for mass production from the beginning. The system did not represent the theoretical optimum solution. It represented the solution that could be manufactured by existing American industry, maintained by trained technicians, and operated by bombardiers with 3 months of training. The design assumed adequate rather than perfect performance, reliability rather than theoretical elegance, and standardization rather than customization. For German engineers, this represented an incomprehensible approach to precision instrumentation. The discussion continued over subsequent weeks. Holloway, within security restrictions, described aspects of American aviation technology that German engineers found increasingly difficult to reconcile with their understanding of industrial capability. The B-17 bomber, he explained, was not designed as an optimal aircraft. It was designed for mass production. Boeing's Seattle plant could produce 16 B-17s daily using assembly line techniques adapted from automotive manufacturing. Each aircraft contained engines, instruments, and systems manufactured by multiple suppliers to standardized specifications. Any B-17 could accept any replacement engine from the supply system. This interchangeability, achieved through precision manufacturing across multiple facilities, exceeded German aircraft production capability. German aircraft production, the engineers knew, emphasized performance optimization over production efficiency. Each Messerschmitt Bf 109 required skilled craftsmen for final assembly. Engines were individually fitted and tuned. Replacement parts often required hand-fitting. This approach produced superb individual aircraft but limited production capacity. Germany produced approximately 33,000 Bf 109s during the entire war. America produced 12,731 B-17 seconds alone, plus additional thousands of B-24s, B-25s, and other bomber types. The statistical disparity forced a question that German engineers had been avoiding. If American industry could produce precision aircraft in such quantities, what other capabilities had German intelligence underestimated? The question became urgent during autumn 1945 when Camp Butner received technical journals and magazines as part of the post-war educational program for prisoners. Aviation Week, Machine Design, and similar publications contained articles describing American aviation technology in detail now that wartime security restrictions were lifting. The optical engineer from Zeiss, reading a technical description of the Norden Bombsight's optical system, made calculations in the margin of the magazine. The stabilized telescope, according to the article, maintained optical alignment within 3 arc minutes while the aircraft maneuvered. The gyroscopic stabilization system used a 50-pound flywheel spinning at 10,000 revolutions per minute. The analog computer solved differential equations in real time using mechanical components, gears, cams, and differentials machined to tolerances measured in 10,000ths of an inch. The engineer showed his calculations to colleagues. For such a system to function reliably under combat conditions, every component required precision manufacturing: the gyroscope bearings, the optical lens system, the mechanical computer components, the stabilization platform, all demanded manufacturing precision that exceeded anything in his experience. More significantly, maintaining such precision across thousands of units, manufactured by multiple suppliers, installed in aircraft built in different factories, represented an industrial achievement that seemed impossible. Yet the evidence was undeniable. American bombers had conducted precision raids throughout Germany. The targeting accuracy was documented. The technology existed and functioned as described. The realization came gradually through accumulated evidence rather than sudden revelation. German engineers began requesting technical journals, reading articles about American manufacturing methods, quality control systems, and production techniques. They discovered a technical literature that emphasized practical problem-solving over theoretical elegance, standardization over optimization, and reliability over performance limits. The philosophical approach pervaded American technical culture. German technical literature sought optimal solutions to specific problems. American technical literature sought adequate solutions to general problems, solutions that could be implemented widely rather than perfectly in specific cases. The Norden Bombsight's development history, revealed through declassified documents and technical publications available to prisoners by late 1945, exposed assumptions that German military intelligence had never questioned. Carl Norden, a Dutch engineer working in America, began development in 1923. The United States Navy funded initial research seeking a solution to the fundamental problem of high-altitude bombing, calculating the precise release point for a bomb traveling in a parabolic arc while the aircraft moved at speed and altitude through variable wind conditions. The mathematical problem was straightforward. The engineering challenge of creating a mechanical device that could solve these equations in real time under combat conditions, while remaining simple enough for mass production, had seemed insurmountable. Norden's solution embodied American engineering philosophy completely. Rather than creating a theoretical optimum, he designed a system that distributed complexity across multiple simple components. The bombsight consisted of three primary subsystems: a stabilized optical sighting mechanism, a mechanical analog computer, and a gyroscopic platform maintaining level reference regardless of aircraft attitude. Each subsystem was mechanically complex but conceptually simple. The optical telescope, mounted on a gyro-stabilized platform, allowed the bombardier to track the target visually. The mechanical computer, accepting inputs for altitude, airspeed, wind direction, and bomb ballistic characteristics, calculated the trajectory. The gyroscopic platform maintained a stable reference frame independent of aircraft movement. German engineers examining technical descriptions recognized immediately that no single component represented revolutionary technology. Stabilized optical platforms existed in German fire control systems. Mechanical computers were used in German naval gunnery. Gyroscopic stabilization was understood and implemented in various applications. The revolutionary aspect was integration. Norden had created a system where three moderately complex subsystems worked together to achieve a result that exceeded what any single complex system could accomplish. More significantly, each subsystem could be manufactured separately, tested independently, and assembled into a complete unit using standardized procedures. This modular approach enabled mass production while maintaining precision. The analog computer component particularly fascinated the mechanical engineers. The device used a series of gears, cams, and differentials to solve ballistic equations mechanically. A bombardier input altitude using a dial connected to a gear train. Airspeed input came from the aircraft's pitot-static system, transmitted through mechanical linkages. Wind correction required the bombardier to observe drift and adjust a correction dial, which mechanically altered the computer's calculation. The bomb's ballistic coefficient, predetermined for each bomb type, was set using interchangeable cams that modified the trajectory calculation. The mechanical computer continuously calculated the solution, outputting the precise moment for bomb release through an electromechanical trigger circuit. The engineering elegance was undeniable, but what impressed German engineers more than the design was the manufacturing philosophy that made the design possible. Each gear in the mechanical computer required precision machining to tolerances of 3/10,000ths of an inch. In German manufacturing practice, if you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Such precision required skilled craftsmen using precision measuring instruments. American manufacturing achieved such precision through process control rather than individual skill. The gears were cut using specialized machines that held tolerance automatically. Quality control used statistical sampling rather than individual inspection. The manufacturing process assumed that if machine setup was correct, all parts produced would meet specification. This assumption, verified through statistical quality control methods, enabled production rates that individual craftsmanship could never achieve. Camp Swift, Texas, received a group transfer from Camp Butner in December 1945 that included several of the technical specialists. Among them was Hauptmann Fischer, whose observation of high-altitude bombing accuracy at Stalag Luft Three had initiated his questions about American bombardment technology. At Camp Swift, Fischer volunteered for work at the camp's aircraft salvage operation. The facility processed damaged aircraft returning from training missions, recovering usable components and materials. The work provided Fischer with direct access to American aviation technology, including, on one occasion, a damaged B-17 that contained an intact Norden Bombsight. Security protocols required removal of classified equipment before aircraft reached salvage facilities, but battlefield damage had made one bomb site inaccessible to recovery crews. The device remained in the damaged nose section when the aircraft arrived at Camp Swift's salvage yard. Fischer, working as part of the salvage crew, observed American technicians extracting the bomb site using cutting torches to access the jammed equipment bay. The operation took 3 hours and resulted in the bomb site's complete destruction, but Fischer observed enough to confirm the technical descriptions he had read. The device was smaller than he expected, approximately the size of a large typewriter. The construction was robust rather than delicate, designed to withstand combat conditions. Most significantly, the manufacturing quality was consistent with mass production rather than individual craftsmanship. The destroyed bomb site was transported to a secure disposal facility, but components remained in the salvage yard long enough for Fischer to examine manufacturing details. The gear teeth showed precision machining marks consistent with automated production. The optical components, though damaged, revealed lens coatings and assembly methods indicating standardized manufacturing. The gyroscope housing, cracked open by cutting torch, showed bearing races machined to tolerances he estimated at 5/10,000ths of an inch. Every detail confirmed that this device, capable of precision bombing from 25,000 feet, had been mass-produced using industrial methods that prioritized consistency over individual perfection. Fischer's report to fellow technical prisoners, shared during evening discussions in camp barracks, catalyzed a broader realization. The Norden Bombsight was not exceptional within American military technology. It was representative. If America could mass-produce precision bomb sights, maintaining tolerances of 10,000ths of an inch across production runs of thousands of units, what other technologies had achieved similar production scale? The B-29 bomber, articles mentioned, contained a sophisticated analog computer for engine management. Radar systems, increasingly discussed in technical publications, required precision electronics manufactured in quantities exceeding 50,000 units. Proximity fuses for artillery shells contained miniature vacuum tubes and mechanical components that had to survive 15,000 G-forces during firing, manufactured in quantities of millions. The statistical evidence accumulated into an unavoidable conclusion. American industrial capacity had achieved precision mass production at a scale that German industry never approached. This capability was not limited to a few exceptional programs. It pervaded American military production. The implications extended beyond immediate military technology to fundamental questions about industrial philosophy and economic systems. How had America developed such capability? What economic conditions enabled such investment in precision manufacturing infrastructure? Why had German intelligence so completely underestimated American industrial capacity? The answers emerged through conversations with American supervisors, reading American technical literature, and observing American management methods. American industry, the engineers discovered, had spent the 1930s developing mass production methods for increasingly complex products. The automotive industry, forced by Depression-era price competition to improve efficiency, had pioneered quality control methods that enabled precision manufacturing at scale. Statistical process control, developed by Walter Schuhart at Bell Laboratories, provided mathematical methods for maintaining quality without individual inspection. This methodology, adopted widely by American manufacturing, created production systems where precision emerged from process control rather than individual craftsmanship. The cultural implications were as significant as the technical details. American technical education emphasized problem-solving over theoretical perfection. American engineers were taught to find adequate solutions that could be implemented rather than optimal solutions that remained theoretical. This pragmatic approach, which German engineers had dismissed as intellectually inferior, had produced practical results that theoretical elegance could not match. The Norden Bombsight was not the theoretically perfect solution to high-altitude bombing. It was a solution that worked, could be mass-produced, and achieved sufficient accuracy for military purposes. This sufficiency, achieved at scale, defeated theoretical perfection achieved in limited quantities. The bombing accuracy itself became a topic of intense discussion among German technical prisoners. Published accounts, now available in camp libraries, documented 8th Air Force bombing campaigns over Germany. The statistics were precise and verified. From altitudes exceeding 24,000 feet, American bomber formations consistently placed 50% of bombs within 1,000 feet of the aim point. Under optimal conditions, with experienced bombardiers and clear weather, accuracy improved to 50% within 400 feet. These statistics, compared against German bombing accuracy over Britain, revealed dramatic disparities. German bombers, operating at lower altitudes with less sophisticated bomb sights, achieved 50% accuracy within 1 mile under comparable conditions. The accuracy advantage translated directly to military effectiveness. American bombers could target specific industrial facilities rather than general urban areas. The ball-bearing factories at Schweinfurt, the aircraft production facilities at Regensburg, the oil refineries throughout Germany, all received precision attacks that degraded specific capabilities. German air defense, designed to protect general areas, struggled to concentrate forces when attackers could strike precise targets throughout a broad industrial region. The strategic impact of precision bombing exceeded simple damage calculations. It forced dispersal of German industry, imposed protection requirements that exceeded available resources, and created logistical complications that reduced overall production efficiency. Fischer, analyzing published bombing accuracy data, calculated the mathematical implications of precision from 25,000 feet. At that altitude, a circular error probable of 400 feet represented an angular accuracy of approximately 0.1 degrees. Achieving such accuracy required the bombsight to maintain optical alignment within 3 arc minutes, to calculate ballistic trajectories accounting for altitude, airspeed, temperature, and wind drift, and to trigger release at precisely the correct millisecond. The mechanical analog computer solved these calculations continuously, updating the solution 30 times per second, compensating for aircraft movement, and changing flight conditions. The computational power, achieved through mechanical means in a device weighing 60 pounds, represented an engineering achievement that German military technology had not attempted. The gyroscopic stabilization system particularly impressed the hydraulics specialist from Heinkel. The stabilization platform maintained level reference independent of aircraft attitude, allowing the bombardier to track targets visually, while the aircraft maneuvered during the bombing approach. The gyroscope, spinning at 10,000 revolutions per minute, generated sufficient angular momentum to resist aircraft rotation. Precision bearings, manufactured to tolerances of millionths of an inch, enabled the gyroscope to spin continuously for hours. without degradation. The entire stabilization system operated reliably at altitudes where temperatures reached 40 degrees below 0 Fahrenheit, where atmospheric pressure was 1/3 sea level, and where vibration from 4 Wright cyclone engines created a hostile mechanical environment. American technical literature described the Norden Bombsight's operational requirements with casualness that German engineers found remarkable. The device required pre-flight calibration taking approximately 15 minutes. Bombardier training emphasized systematic procedures rather than technical understanding. The training course, lasting 12 weeks, produced bombardiers capable of operating the system effectively without understanding the underlying mathematics or mechanical principles. This separation of operation from understanding represented another aspect of American technical philosophy. Complex systems could be operated by adequately trained personnel following standardized procedures. Deep technical knowledge was concentrated in design and maintenance specialists, not distributed among all operators. The maintenance philosophy similarly emphasized standardization over expertise. Norden bombsights were maintained using modular replacement rather than component repair. If the optical system failed, the entire optical assembly was replaced. If the analog computer malfunctioned, the computer module was swapped for a functional unit. Failed components returned to depot-level facilities for repair by specialists. This maintenance approach required extensive supply systems and spare parts inventory, but enabled quick aircraft turnaround and reduced field maintenance complexity. German maintenance philosophy emphasized field repair by skilled technicians, minimizing supply requirements but increasing maintenance time and requiring higher skill levels among field personnel. By early 1946, the German engineers at various camps throughout America had accumulated sufficient information to understand not merely the Norden bombsight's technical characteristics, but the industrial system that made it possible. The device represented the visible product of an industrial philosophy fundamentally different from German practice. American industry prioritized mass production efficiency over individual product optimization, standardization over customization, and adequate performance achieved at scale over perfect performance achieved in limited quantities. This philosophy, applied systematically across military production, had created quantitative advantages that overwhelmed German qualitative superiority in individual weapon systems. The realization carried implications beyond immediate military technology. If American industrial philosophy achieved such results in military production, what did that suggest about American economic capacity generally? The prisoners had witnessed American material abundance in camp conditions, regular meals in quantities that seemed unlimited, consumer goods available even during wartime, and infrastructure maintained despite military demands. These observations, combined with understanding of American industrial methods, revealed an economic system operating at a scale that German economic planning had never considered possible. The educational programs implemented in prisoner camps during 1946 provided German engineers with systematic exposure to American technical literature that had been unavailable during the war. Camp libraries received subscriptions to technical journals, including Machine Design, Aviation Week, and Industrial Engineering. These publications, no longer constrained by wartime security restrictions, published detailed articles describing American manufacturing methods developed during the war. German engineers discovered that the Norden bombsight represented just one example of precision mass production techniques applied across American military manufacturing. Proximity fuses contained miniature vacuum tubes and mechanical components manufactured in quantities exceeding 20 million units. Radar systems required precision electronics produced in numbers that exceeded total German electronics production. Even basic items like military vehicles incorporated manufacturing precision that German industry reserved for specialized equipment. The proximity fuse particularly fascinated German engineers because it represented an impossible combination of precision and scale. The device, small enough to fit inside an artillery shell, contained a miniature radio transmitter and receiver, vacuum tubes, batteries, and a mechanical safety system. The entire assembly had to survive being fired from artillery pieces, experiencing accelerations exceeding 15,000 times gravity, then function reliably to detonate the shell near its target. American industry manufactured these devices in quantities exceeding 20 million units between 1943 and 1945. Each unit required precision assembly of components manufactured to tolerances measured in thousandths of an inch, all achieved through mass production methods that prioritized quantity without sacrificing quality. German engineers analyzing these production statistics confronted an uncomfortable question. Why had German military intelligence so completely underestimated American industrial capacity? The answer emerged through discussions among technical prisoners and reading of American industrial history. German intelligence had assessed American industry based on peacetime production patterns and theoretical capacity calculations. They had assumed that American industrial organization, dominated by private corporations rather than state planning, would prove inefficient under wartime demands. This assumption was not unreasonable based on German experience, where centralized planning coordinated industrial production. The assessment failed to account for American industrial culture, which emphasized practical problem-solving, rapid adaptation, and distributed decision-making. The transformation of American industry between 1941 and 1945 demonstrated capabilities that centralized planning had not predicted. Ford's Willow Run plant, built specifically for B-24 bomber production, achieved production rates of 1 bomber per hour at peak output. The facility covered 67 acres under one roof, employed 42,000 workers, and produced 8,655 bombers between May 1942 and June 1945. This production rate exceeded total German four-engine bomber production during the entire war. More significantly, the B-24 seconds produced maintained consistent quality despite production speed. Interchangeable parts allowed any component to fit any aircraft. Standardized assembly procedures enabled workers with minimal training to achieve precision that German craftsmen required years to develop. Hauptmann Fischer, transferred to Fort Dix, New Jersey for repatriation processing in April 1946, reflected on his journey from Stalag Luft Three's frozen compound to understanding of American industrial capacity. The bombing accuracy he had witnessed from the ground in February 1945 had seemed impossible based on his engineering knowledge. His subsequent exposure to American manufacturing philosophy explained not merely how such accuracy was achieved, but why German intelligence had failed to predict it. The Norden Bombsight was not a technological breakthrough in the sense of revolutionary innovation. It was an engineering achievement in the sense of practical implementation. American engineers had taken existing technologies, gyroscopes, optical systems, mechanical computers, and integrated them into a device that could be mass-produced and operated by adequately trained personnel. The distinction mattered profoundly. German engineering education emphasized theoretical understanding and optimal solutions. Students learned to calculate the theoretically perfect answer to engineering problems. American engineering education, Fischer discovered through conversations with American technical personnel, emphasized practical problem-solving and adequate solutions. Students learned to find answers that worked within real-world constraints of manufacturing capability, operational requirements, and economic limitations. This pragmatic approach, which German engineers had dismissed as intellectually inferior, had produced weapons systems that defeated German theoretical superiority through sheer quantity and reliability. The statistical disparity was undeniable and documented in publications now available to prisoners. America produced 297,000 aircraft during the war. Germany produced 119,000. America produced 88,000 tanks. Germany produced 46,000. American naval construction exceeded Axis naval production by factors approaching 10 to 1. These quantitative advantages, achieved while maintaining quality standards that enabled interchangeability and standardization, reflected industrial capacity that German war planning had not anticipated. The capacity emerged not from superior technology, but from superior manufacturing philosophy and industrial organization. Repatriation ships departing New York Harbor in spring and summer 1946 carried German engineers who understood that their defeat was not merely military but industrial and philosophical. The technical discussions in camp machine shops, the exposure to American manufacturing methods, and the access to technical literature had provided education that exceeded what German universities offered. These men returned to a devastated homeland where industrial infrastructure was destroyed, where manufacturing capacity was deliberately dismantled as reparations, and where reconstruction required starting from foundations. They carried with them knowledge of American methods that would influence German industrial recovery. The influence is difficult to quantify precisely because post-war German industrial development drew from multiple sources, including Marshall Plan assistance, technology transfers, and indigenous innovation. However, documented cases exist of former prisoners of war who applied American manufacturing methods in rebuilt German factories. Quality control methods, based on statistical process control, pioneered by American industry during the war, appeared in German manufacturing during the 1950s. Modular design philosophy, emphasizing standardization and interchangeability, became increasingly common in German industrial products. The emphasis on adequate solutions achieved at scale, rather than optimal solutions achieved in limited quantities, gradually influenced German engineering culture. Fischer himself returned to Daimler-Benz, which was rebuilding automotive production in Stuttgart. His personnel file, preserved in company archives, notes his prisoner of war experience and subsequent assignment to production engineering. Company records from 1950s document Fischer's advocacy for statistical quality control methods and his emphasis on design for manufacturing, concepts that became standard practice in German automotive industry. While direct causation cannot be established definitively, the correlation between prisoner exposure to American methods and subsequent German industrial practice is documented across multiple industries and companies. The optical engineer from Zeiss returned to find the company divided between East and West Germany, with primary facilities in Soviet-occupied territory. He relocated to West Germany and joined the reconstituted Zeiss operation in Oberkochen. His experience with American optical manufacturing methods influenced the company's post-war approach to precision optics production. Zeiss had traditionally emphasized individual craftsmanship and custom production. The post-war company, competing in international markets, adopted increasingly standardized production methods that enabled higher volumes while maintaining precision. Again, direct attribution is impossible, but the timeline and technical approach suggest influence from engineers exposed to American methods during captivity. The broader impact extended beyond individual companies to German technical education. Universities rebuilding engineering programs incorporated American textbooks and teaching methods. The emphasis shifted gradually from pure theoretical understanding to practical problem-solving. Laboratory work received increased emphasis relative to theoretical lectures. These changes reflected multiple influences, including occupation authority recommendations and Marshall Plan educational programs. But former prisoners of war teaching at technical universities contributed to this evolution. Their first-hand exposure to American technical culture provided models for reformed German engineering education. The Norden Bombsight itself became obsolete rapidly after the war. Radar bombing systems, developed late in the conflict, provided all-weather capability that optical bomb sights lacked. By the early 1950s, precision bombing increasingly relied on electronic systems rather than optical mechanical computers. The bomb sight that had so impressed German engineers was relegated to museums and historical collections. However, the manufacturing philosophy it represented, precision mass production achieved through process control and standardization, continued influencing industrial development throughout the Cold War and beyond. The story of German engineers encountering American precision bombing technology ultimately transcends the specific device. The Norden Bombsight was the visible manifestation of an industrial philosophy that German military planning had not understood. American industrial capacity was not based primarily on technological superiority, though American technology was certainly adequate. It was based on manufacturing philosophy that prioritized scalability, standardization, and distributed complexity. These principles, applied systematically across industrial production, created quantitative advantages that overwhelmed German qualitative superiority in individual weapon systems. Fischer's observation from Stalag Luft Three's frozen compound in February 1945, watching bombers at 24,000 feet achieving accuracy that seemed mathematically impossible, was the beginning of understanding rather than the end. The subsequent months in American captivity provided education in industrial philosophy that German universities had not offered. He learned that theoretical perfection mattered less than practical implementation, that adequate solutions achieved at scale defeated optimal solutions achieved in limited quantities, and that engineering excellence was measured not in individual brilliance but in systematic capability. The psychological impact on German engineers was profound and lasting. They had been educated to believe that German technical training represented the world's finest, that German engineering produced superior products, and that German industrial capability exceeded that of nations lacking Germany's technical tradition. American captivity demonstrated that engineering excellence took forms they had not recognized: the casual abundance of precision equipment in a prison camp machine shop, the mass production of devices requiring tolerances measured in 10,000ths of an inch, and the operational success of weapon systems designed for adequate performance rather than theoretical optimum, all contradicted their engineering education. The contradiction was not resolved through admission of German inferiority, but through recognition of different approaches to engineering problems. German engineering emphasized individual product excellence, theoretical understanding, and optimization. American engineering emphasized production efficiency, practical implementation, and standardization. Neither approach was inherently superior. Each reflected different economic conditions, industrial organization, and cultural values. German engineering produced excellent individual products. American engineering produced adequate products in quantities that created overwhelming advantage. The war demonstrated that in industrial conflict, quantity of adequate solutions defeated quality of optimal solutions. This realization influenced post-war German industrial development profoundly. The economic miracle of the 1950s and 60s incorporated lessons learned partly through defeat. German industry maintained its emphasis on quality and precision, but adopted American manufacturing methods that enabled production scale. The combination, German engineering tradition applied through American manufacturing philosophy, created industrial capacity that made West Germany an economic powerhouse. Former prisoners of war who had witnessed American methods during captivity contributed to this synthesis, though their influence was one factor among many in post-war German recovery. The Norden Bombsight, gathering dust in museums, stands as physical reminder of this historical moment when German engineers confronted the limits of their assumptions. From 25,000 feet, in conditions that German ballistics calculations suggested would prevent precision, American bombardiers using mass-produced optical mechanical computers placed ordnance within hundreds of feet of aim points. The accuracy was not theoretical, it was operational and documented. The devices achieving this accuracy were not custom instruments built by master craftsmen. They were mass-produced units manufactured by the thousands, maintained by technicians with standard training, and operated by bombardiers who understood procedures rather than theory. Hauptmann Klaus Fischer, standing in that frozen compound in February 1945, could not have imagined that his question about bombing accuracy would lead to fundamental reconsideration of engineering philosophy. He observed an impossible result and sought explanation. The explanation revealed not merely technical details, but an entire industrial approach that German military planning had underestimated. His journey from observation to understanding, shared by thousands of German technical prisoners, represents a historical moment when engineering certainty confronted contrary evidence and was forced to evolve. The precision bombing that seemed impossible from the ground was achieved through methods that seemed inadequate from German engineering perspective, yet the results were undeniable. In that gap between expectation and reality lies the story of how engineering philosophy shapes industrial capacity and ultimately determines military outcomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.